Welcome, fellow chemists, to the final video on the reactions of the alkynes. Please send your suggestions my way, as I have not yet settled on a new series. Today we will take a closer look at hydrogenation. The video on the reactions of the alkenes provides useful background information. I bet you have already watched it, but here's the link in case you haven't. Hydrogenation of an alkene was pretty straightforward as long as we had the right metal catalyst. Of course, with an alkene, addition only occurs once. If you think the basics are the same if we have an alkyne, then you're correct. After the first addition we have an alkene, and because the metal catalysts are so effective, this alkene reacts as well. But if you really wanted to stop with an alkene, then you're in luck, because clever chemists have developed different catalysts which prevent the second addition. Chemists have figured out not only how to get it to stop with an alkene, but also how to favor one isomer over the other. Lindlar's catalyst is used to produce cis alkenes. The components of it are on the screen, and you can find out how it is prepared using the link in the description. Aside from this, the previous description of the mechanism is more than sufficient to understand what happens. Hydrogen and the alkyne adsorb to the metal catalyst. They bond when they meet up, and since the hydrogen always meets the molecule from the same side, the addition occurs on the same side. So with hydrogen added to the same side of the molecule, the product is a cis alkene. But the catalyst is still there, so why doesn't it react again? The palladium metal in Lindlar's catalyst is considered poisoned, which renders it ineffective at reducing alkenes, so the reaction is finished. The production of transalkenes does not require the use of a precious metal catalyst. It still requires a metal, but lithium or sodium can be used. In either case, you'll need liquid ammonia as the solvent, so how does it work? First, the metal's s orbital electron reacts with the alkyne to produce something we haven't seen. The lone electron on the right indicates we have a radical, and the charge on the left means it is an anion. Put them together and we have a radical anion. This anion is also a strong base, which means it is a proton acceptor. Luckily, the solvent ammonia provides plenty of protons. So we've lost the ion but retained the radical, and when it is on an sp2 carbon, it is called a vinylic radical. Another sodium atom loses an electron, and this time the vinylic radical becomes a vinylic anion. You may know what will happen next, but do you know that this ion is responsible for the trans product? The reason is alkenes are more stable if the alkyl groups on the double bond are as far from each other as possible. Measuring the distance between the R groups in the cis and comparing it with the trans, the result clearly shows the alkyl groups are more separated in the trans. This means it's the more stable one and favored at equilibrium. Finally, all that's left is for the vinylic anion, also a strong base, to get its proton, which it can by removing it from another ammonia. The result is a transalkene. So do terminal alkynes behave any differently? Using a precious metal catalyst like platinum, a terminal alkyne becomes a terminal alkene, and after a second addition, an alkane. If you want to avoid the second addition and get that terminal alkene, then either of the special catalysts should suffice. Notice I did not classify the alkene as cis or trans. That's because this is all that changes. Since the right sp2 carbon bonds to identical substituents, the alkene cannot be classified as cis or trans. In summary, complete hydrogenation of an alkyne with traditional metal catalysts will produce an alkane. The process can be stopped at the alkene stage in two ways. First, using Lindlar's catalyst to produce the cis alkene. Next, using lithium or sodium in liquid ammonia to produce the transalkene. On terminal alkynes, complete hydrogenation with traditional metal catalysts generates an alkane. The specialized catalyst will stop at the alkene stage. Regardless of exactly where the hydrogens land, we still cannot classify it as cis or trans. Coming up, the nomenclature of ketones and aldehydes. Thank you very much for watching. If you enjoyed this video, please like and subscribe as I have more in development. With a ketone and aldehyde video coming up, here are two reactions involving them.